Hi, everybody. Good evening. Uh, Welcome again to Rod's Office Hours, where we talk about practical applications and oil industry insights. This week, we're going to talk about probability of success relating to the oil and gas industry. I think, and I want to jump right into this because there's quite a bit to cover when we're talking about probability. And I use the term probability. We'll define that a little bit. Think on chance of success. Think on, may the odds ever be in your favor. You may have heard that expression. If you're rolling dice, what's the chances of getting a certain number? There's lots of games and that sort of thing that require probabilities. There's a probability distribution, like a normal distribution. Lots of things in nature are distributed normally or log normally, and you can use that to our advantage when dealing with uncertainty. And that's one of the things that I call it the science of probability, the math of probability, helps us deal with is uncertainty in oil and gas exploration, drilling, and operations. Because a lot of the times, almost never do we know the exact answer. All we can do is get a range. So we have to deal with that uncertainty, and using probabilities allows us to do some of that. This image here in the middle was actually the price of oil. Median $82 a barrel, but there's a range of what it could be based on different factors. And of course, for exploration drilling, we don't want to have this sort of picture like from the old days when they had oil gushing over the top of the drilling derrick. These days we call that a blowout, but we are trying to maximize our chances for getting oil and gas. So we're going to talk about how to use probabilities to help us make decisions and choices to get to that goal. A bit about me, just a reminder, my name is Rod Gibbons, petroleum engineer, and I've been an entrepreneur in the industry. Working with my wife, Willow, we've had a couple of different companies and in different countries. And we, again, focusing on engineering and equipment supply and all aspects of oil and gas. So I got a bachelor's degree in mechanical engineering. I'm not a professor by any means. I don't have a master's, any of that sort of stuff. But I'm just here. I've been 30 years in the industry, just to give how I've applied some of these lessons over the years. So that's what we're going to focus on. If you have any questions, there's a Q&A tab on the webinar. You just type them in there as we go, and I'll try and address them as we go. That really helps direct. You get a chance to direct where we take this thing. Probability and statistics. So just going to do a little bit of theory, like one slide of theory. And so you hear these terms kicked around a lot together, probability and statistics. Well, they are super related. Probability predicts the likelihood of a future event based on known parameters. So you know what you're dealing with, and you want to see what's going to happen in the future. Statistics, you're looking at you're analyzing past data to try and figure out what the underlying rule is, in order to make broader conclusions. So there's a couple of different ways of showing this, but you have a model, you have an idea of how the world works. You predict what's going to happen using probability. Then you get data. That data you can use statistics to better refine the model. So And an example of that is flipping a coin. We're going to use that example here quite a bit. So, and the thing that's great about a coin is it comes up heads or tails. There's a 50-50 chance you're going to get one or the other. And so if the coin is fair, then you should get half the time heads, half the time tails. That's the probability is 50%. If a coin is biased or if a dice is loaded, then you're going to get skewed results. And so your probability model would have to be different. And then same sort of thing, if you look at what the data is, you can come up with a model. So again, probability and statistics, you'll hear them interchangeably. They're basically going forwards or going backwards on the same sort of data and the same sort of models. Statistics are important, but I'm going to talk more about probability because we're more interested in predicting what's going to happen when we're dealing with our uncertainties. So how do we calculate probability? So the simple example that we'll start with is flipping a coin. There's a probability of tails is 50%. And how do we get to 50% or 1/2? So here P is the probability of T tails. Probability of tails is equal to 1 in 2 chance. Well, when we look at it, how do we calculate it is the number of possibilities to satisfy a condition divided by the total number of possibilities. So for a coin, it's 1 in 2. If you're rolling a dice that has 6 sides, it's 1 in 6 because there's one possible condition out of 6 entire number of possibilities. So that's probability. So you can count 1 out of 2 and then, okay, well, that's 0.5 or 50%. So that's somewhat useful, I guess. But when you look at it, what's really cool about it is you can use it for more and more complicated situations. So when you're flipping a coin, you start off here, and this is like a probability tree, if you think about it, or a decision tree, but we're not making any decisions, this is outcomes. So we start off here, we flip our coin, like Fred and Barney here, and there's a 0.5% chance, or 0.5 is going to be heads, 0.5 is going to be tails. Once we get that first flip, now the second flip is 0.5, it could be heads, 0.5, it could be tails. Because once this flip is done, the coin doesn't remember what happened to it. So this is, again, entirely independent. And same thing when we do tails. 0.5 is tails, or heads, 0.5 is tails. So you can see, we branch it out. For 2 flip tosses of the coin, our outcomes is heads, 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 tails, tails, heads, and tails, tails. So there's there's a combination of 4 different things. So calculation-wise, so when this goes together in this tree, what I'm going to do is I'm going to go, okay, the probability of getting heads and heads is actually 0.5 times 0.5. Here's calculation, 0.5 times 0.5 equals 0.25. Then same thing, the probability of heads and then tails is 0.5 times 0.5, 0.25. Same, 0.25, 0.25. Then these end branches here, this always adds up to 1. That's how you know, okay, the probabilities are correct. Because there's always 100% chance I'm going to get one of these outcomes. There's no other way for these outcomes to line up. I can't get heads and nothing. I have to get either way. There's a probability of one. It's certain that I'm going to get one of these outcomes. So this is a simple model, but if we remember these kind of rules, that when you have two independent things happening, you can multiply them to figure out what the probability is. That really starts to be useful. So we use it in a decision tree. So what's it useful for? Well, it's useful for a bunch of math if you wanted to do that, but we're not interested in that. We're interested in how can we use it with our business. So we set up these things called decision trees. So here's the decision. This is for a software application. A software company can decide to develop a game app that costs $80,000. Or they can develop a productivity app that costs $60,000. Or they can revamp an existing app they have, and that's $30,000. So it's minus 80, minus 60, minus 30. Okay, so what they're looking for, what outcomes they're looking for. So they do that. Say they develop a game app, then you get large revenue or small revenue. And what they have estimated is that there's a 35% chance of getting a large revenue and a 65% chance of getting a small revenue. And what's large and small? Large is $250,000, small is $150,000. Then if they go with a productivity app, they do the same analysis. And they say a large revenue is 60% chance of getting that and 40% chance of getting a small revenue. So it's a bit better odds of getting a large revenue here. It went from 35 to 60. But a large revenue in the productivity app is $200,000. And the small revenue is $120,000. And then same thing with existing, revising their app. A large revenue, 58%, 150,000. Small revenue, 80,000. So, okay. So now I don't know what decision to make here. I don't know what the right answer is. I see a bunch of outcomes. Well, what I'm able to do, because we have that probability, is I can take these things, and if I'm putting them in line, I can multiply them. So I go expected value. What's the expected value of developing a game app? Well, I could be on the large revenue side, which is 250 times 35%. Or, so I'm multiplying because I'm going this way. And then I'm going to add, so I go to 250 times 35%. And then I'm going to do 150,000 times 65%. So I'm risking I'm risking 150, 65%, and I'm risking 250,000, 35%. Then I'm going to subtract $80,000. That's a known. I know I'm going to spend that. So then my expected value on this branch, when you look at the math here, is 105,000. Again, what my outcome is times my probability of getting there. That's how I get that value. And then I'm adding it to the other branch, to this node, and then adding it to whatever the cost is. So here I'm at 105. I do the same math for this middle one, it's 108. And I do the same one down here, and it's 90,000. So actually, from an expected value point of view, developing the productivity app will actually be the preferred solution. But it's also pretty close to the game app, so there could be some maybe you got to bring in another constraint. But definitely the revamping the existing app is a lot lower. So that's how we use expected value from a decision tree. But again, it's the same as when we flipped a coin. We just multiplied the probabilities. Why is this important? Why do we care? Well, if we're an exploration and production company, why we care is because this is our business cycle. So we start off obtaining licenses, exploration licenses. That gives us access so that we can drill onshore or offshore. Then we conduct geology and geoscience to see what the potential is. This is our workflow here. Then the next thing we do is we explore and we appraise. Here we've discovered oil and gas. Then we develop it. This is called the greenfield. So meaning we've explored it. Now we've got to put a new facility in a green field. Then as the facility and the equipment matures, then you have brownfield costs, projects that you have to do. Think on maintenance or a little bit of debottlenecking or trying to make things better. That's in your producing phase. So in our producing, we're producing gas and we get revenue. Now, some of that comes off because we have operations costs. So this comes in and goes into our producing again. But once we go net of operating costs, then we pay taxes on and royalties on the production and the income. We have to pay interest on whatever capital we borrowed to do this, to get this facility up and running. For public companies or shareholders, we'll pay a portion of dividends so that the shareholders get some value. And then we'll either pay off some debt or take on some new debt, depending on what we need for our activities. Then we'll reinvest that, whatever's left, then gets reinvested back into these activities. So when we're doing licenses, G&G, exploring and appraisal, these are all items which have a high degree of uncertainty. So we have to use, there is some uncertainty in saying the costs and the activities here, but here the outcomes are uncertain. And that is the sort of engine that's driving our business. So that's why probability and managing uncertainty is super important in the oil and gas industry. So, and if we talk specifically on exploration wells, the good thing about flipping a coin, heads or tails, is that we know that the probability is 0.5 or 0.5. That's I would say a given. Again, if you were to flip it 1,000 times and it didn't work out like that, then you've got statistics where you can actually update these numbers. But no one wants to sit around flipping a coin all day. But this is a very simple system, heads or tails. In exploration drilling, it's a more complicated system, but luckily, when we look at probabilities, there's actually only 4 parameters which is going to affect our exploration success. Or you may hear chance of success, COS, or POS, probability of success. What's our POS on this drill? Well, is it 10% or 80%? You'll hear that sort of words being used. So to get movable hydrocarbon, we need a couple of things. we need structure. So here is the underground, and at the bottom we have organic source rock. So we need a source of oil and gas. Then we need a migration route. That's number 2. Then we need a trap to trap the gas. And we need a porous reservoir and a top seal. And top seal can sometimes be with structure. So those are kind of our main elements. So if we go through those, first we have to have source. We have to have hydrocarbons in the system. And so you see in this cartoon, source rocks buried pretty deep, very hot, and where it gets converted to oil and gas. So in this chart, depending on, so like algae, depending on what the organic material is here, algae, for example, will be more oil prone. Plankton is more oil gas. Land plants are more gas. So depending on what the source material was that was deposited years ago, that'll help determine what type of hydrocarbon is going to be converted into. And so that is deep, very deep, and given time to cook, as they say. So you got to have source. If there's no oil in the system or no gas in the system, then it's very difficult to actually try and drill for oil or gas, because so there's what's the probability that you have source, that you have hydrocarbon in the system? If you have hydrocarbon in the system, if you get past that probability, then you need to have migration. And what migration is, you have these source rocks very deep. Now you need a path for them to flow along. The oil, so the entire subsurface has got water in it, pretty well salt water. When plant material, algae, plankton, get converted into oil or gas, that's lighter than water. So it wants to float up. As long as there's a path for it to flow along, and it could be reservoir rocks, it could be sandstones, or it could be fractures, natural fractures or cracks in the rock where it finds its way through, then it's going to migrate up. Sometimes you can see that when there's no trap, you'll see that surface as a tar or oil seep, but then it can collect along the migration path. And sometimes, and this is why you can have a basin, an area that's got, over here it's got oil, and over here it doesn't. One of the reasons could be when the hydrocarbons migrated up, this area may have been in the what they call the shadow of migration. The oil couldn't get in there and hold up in some areas. It actually missed that area. So you need to have a migration pathway. Again, there's a probability of a migration pathway. Then once the oil is migrating, once it's starting to go towards the surface, again, just because it's lighter than the water, then you need structure. So, and what I mean by you need structures, you need a trap. There's got to be something that stops and captures that oil and gas. And so this is a anticlinal trap. So if you think on a hill, there's a cap rock here in gray, and then the oil and gas collect under that dome. And speaking of domes, salt domes is another way to form a trap. The salt is when you put it under pressure, it almost flows like a liquid. So it'll get pushed up and come out and create a salt dome. Well, around that salt dome, now you've got a trap where the oil and gas can get hung up and stops. A fault trap is where you've got because of during a seismic event, earthquake, the Earth's crust move, and you get a porous zone juxtaposed or next to a non-porous zone, a cap rock. That causes a trap. And again, if you've got oil and it's migrating upwards, and you've got a place to catch it in this trap, that's necessary to get an oil and gas reservoir. And then another one would be a stratigraphic trap, which is just you can see here, it's not faulted. It's just the rocks are changing. The type of rock is changed, and that makes a place for oil and gas to accumulate. So this is a cross section, pencil drawn, but you get the idea when you're looking at seismic or geologic mapping. The dashed line here was before the well was drilled. This is where it looked like on seismic or through interpretation of other features. This is where it looked like the trap was, the structure was. It's an anticlinal hill. After the well was drilled, rather than contacting the reservoir here, it was contacted down here and was probably full of water. Well, the model then needs to be updated. And that's the solid line here. Oh, it's slightly off, it's slightly over. That's why this contact is here. And here is where the oil and gas could be. So what's the probability of success of knowing where this structure is? How good do we know it? And another factor that's needed is reservoir rock. So you can see in this example here in the yellow, you may have had a well that was drilled. We had oil, we had source rock, we had migration. We had a bit of a anticlinal trap here, like a little bump. Encountered oil. Oh, that's great. Then we have a map. Oh, the beta location here. It's further up, and it's also a bit of a bump. Well, that's a good exploration well, you would think. But this is a sandstone or carbonate. This is porous rock. You need to have reservoir. This picture over here, so you can see this is a rock cut, like at a highway. And so this triangle bit here is sandstone. And you can see it pinches out, and then here's shale, which was like a mud that's been turned into shale. Well, if you can imagine that this interpretation is slightly wrong, and it doesn't come back down together like that, but it actually joins together and pinches out. If you drilled here, that's a bad day, because you might have thought that this was going up and this was top of structure, but you drill it and it's not there. There's no reservoir, there's no porosity, there's no reservoir rock. You have to have porous rock or a fracture matrix in order to have movable hydrocarbon. And this is somebody's aquarium. And I want to explain one of the other things when it comes to risk is seal. And so you have, say you have gas in the source rock and it's migrated up and you've got structure. So you've got a trap. And so in this video, this aquarium video, you can see this is an air bubbler here. And so that represents our source rock and our migration path. And this kitchen sieve here, or sieve, is our trap. And one of the things that, so if you imagine that this is actually rock and this is gas, this gas is coming from deep down. It's bringing that, changing that pressure in this nice stable system. There's a thing called capillary pressure, which, so you can see this. So there's surface tension. So this is a sieve. So, but it'll hold air in an aquarium. So because of the surface tension of the air, but then you see once the pressure builds up, it actually releases the gas out of the sieve. Well, if your cap rock is not strong enough, then as it fills up with gas pressure, eventually you get to a point where the cap rock fails and releases the gas out of your trap. But there's still some residual volume left there. There'll still be some gas left there, but it just won't be full because you don't have a great seal. So that's another risk. So, but again, super interesting that you can actually see this with a kitchen sieve in an aquarium. I suspect it's much more dramatic in a gas reservoir, but we can't see that. So those are what physically is happening. When we go back to our probability, our coin flipping exercise, what is the chance of getting heads and heads? It's 0.5 times 0.5 is 0.25, 25%. Probability of success is the probability of the trap, probability of reservoir, probability of migration, probability times probability of source rock, times probability of, they say hydrocarbon preservation here, but it's more seal. So same as we're just multiplying coin tosses here, all of those geologic parameters, we just need to multiply the probabilities together to get our overall probability of success. So here's a bunch of text. This video will be put on our YouTube channel, on Ballycatter YouTube channel. So you'll be able to see, this is just a table from a paper giving what you should use for probabilities in trap, reservoir, source rock, migration, and seal or hydrocarbon preservation, based on what type of reservoir you're dealing with or what type of geologic setting. So sometimes you'll see that structure, algae, reef form is a 1, it's an absolute. Sometimes it's undefined structural network, it's 0.05, it's only 5% chance. So it really depends on what prospects you're looking at, what area you're looking at. But like I say, you should be able to pull this off of YouTube if you need to have a guide to go by. But it is, again, if something is 0.5 times 0.5 times 0.5 times 0.5, the percentage gets very small. The probability gets very small because all those things are multiplied by each other. So it's, and we'll talk about some of those probabilities. So this is some data that I pulled from different papers, different sources about, again, we have our different geologic parameters: structure, reservoir, seal, migration. And what I noticed was my observation on this was different data sets lead to different conclusions. This data set showed that structure was responsible for most dry holes. And so a dry hole, by definition, when you're doing exploration drilling, you either have a successful well or a dry hole. That doesn't mean that there's no liquid in the well or no fluid. It could be that there's either any of those geologic situations happened, or you did find a hydrocarbon, but it's not commercially, it's not economic to actually develop it. Those are also called dry holes. So you might be in a place that there's been a bunch of dry holes drilled, but some might be water wet, some might be no reservoir, some might be hydrocarbon, but not enough volume to make it commercial. They're all called dry holes. And again, over here, this is seal being the highest risk of failure. I guess basically, it depends on the data set, and it depends on the area as to what's the main failure cause. Again, this is a little bit of doing statistics. We're looking at actual data and looking backwards at it, as opposed to trying to predict the future. So we have to make these decisions, and a great tool for doing this is a decision tree. So in this decision tree, this branch is drill well. This branch is shoot seismic first, and then decide to drill or not. So that's a common question that we have when we're doing exploration work. Or actually, I would say in oil and gas, almost any kind of work. Do we take an action, or do we get more data before taking an action? That's a good use of a decision tree. But we're going to use it for exploration work. So in our drill scenario, so we think, yep, we're happy to go out and drill. And we get a producer or we get a dry hole. And 0.5 and 0.5. 50-50. So it's like tossing a coin here on this. The other thing we're saying is, okay, if we shoot seismic, 33% chance, or 0.33 and 0.67 probability. So really, there's a 1 in 3 chance that we actually, after we shoot the seismic and interpret it, we will say we don't want to drill here. There's a 2 in 3 chance that we do want to proceed with drilling, and because we've got more data, because we've got a better seismic image, we think there's an 80% chance we'll get a producer and a 20% chance of a dry hole, which is improved from 50-50. However, to get to here, we have to spend money. So in this example, I think it's $100,000. $100,000 to shoot seismic, plus another $25,000 of deferred income, because it takes time to shoot that before you make a decision and processing. So there's all kinds of trade-offs, but here's a decision tree is a great way to deal with that uncertainty. So we look at our drill scenario. We're going to drill, and we say we drill and we get a producer. So we have economic gas volumes. So it's $800,000 to drill a producer. Well, if the cost is 800,000 and the probability of doing it is 0.5, and we multiply 800 by 0.5, we get 400,000 is the EV expected value here. On the dry hole side, there's a 50% chance we'll get a dry hole. The cost here is only minus 400,000. And the reason for that is if we drill through the formation and we don't find oil or gas, then we're not going to spend the rest of the money to run the completion, to run the artificial lift, to do the tie-in. So the dry hole cost is that's our minimum amount we can spend to find out if we have anything. So that's only 400,000, and you multiply that by 0.5, so that's minus 200. Wrist. Okay, so I'm going to figure out what the value is here, the expected value, I'm going to add these two numbers together. 400 plus minus 200 for the dry hole gives an expected value of $200,000. So we put that here, we just write that down here. We call it rolling it back. We roll it back here to our decision point. So we say, okay, if we decide to drill, the value of that project is expected to be 200,000. It's not going to be 200,000. It's going to be one of these outcomes, but risk-wise, this is the number. Down here, if we were to drill after seismic, it still costs us $800,000 to do it. It also costs $100,000 for the seismic shoot and $25,000 to wait for the processing to be done. Times 80% chance, that puts us at $540,000 on this lake. And then the dry hole cost is only 0.2, because there's only a 20% chance of the dry hole. 400 minus 100 on the seismic shoot is $100,000. We don't take the 25,000 off there because we're not deferring any income. We don't lose that. We don't get anything anyway. So then that gives our expected value 540 minus 100, 440. So that's back to here. But now we're back to this branch. And then we say, okay, if we're going to be drilling, there was a 0.67% chance of drilling times the 440,000 that we spent, or that we expected valued here, that gives us 295,000. Because we're balancing out, there's only a 66% chance we're actually going to drill. Because there's a 33% chance that we'll find enough information during the seismic shoot that we will stop drilling. So that's 0.33 times the 100,000 is minus 33. So we're going to lose 33,000, but it saves us from losing hundreds of thousands. So we have two numbers there. Same thing we do again. We're going to add those two together to get back to our expected value on shooting seismic. And that's 295 minus the 33 gives an expected value of 262,000. So from a risk point of view, using probabilities, we can see that we are economically, financially better off to shoot the seismic will give us an expected value of 260,000 versus just drilling and getting an expected value of 200,000. And a lot of times this is again a close example, but sometimes you'll see that one can be entirely negative. You expect to lose money, so you shouldn't do that branch at all. So but again, the question of to drill or to shoot seismic to gather more data, really, a lot of times it comes down to what the cost differences is between your options, and is the data you're going to get going to materially impact your probability. And so I would say in this example, going from a 50% chance on a producer to 80%, probably the main risk was probably structure. So you're really looking so seismic can really help you with that. to define where the structure is. So if your risk was migration or if it was or reservoir, seismic shoot might not tell you, might not change that number that much. But at least this is a tool that we can use to evaluate it. So decision tree analysis and extension. Pretty question coming in here. Pretty useful tool. Just sorry. Hi Brian, good to see you again tonight. So that's the theory. That's how the geologic uncertainties, we handle it with probabilities. A few slides here now on actual results, so you can think of it more as statistics because we're looking back. And this is old data from 1988. It just happened to be in a paper I was reading. What are the success rates? What's the probability of success? And this is comparing the United States and Canada. And so new pool wildcats was about 53% for US, 48 for Canada. Deeper pool wildcats, only 15% chance in US, 54 in Canada. Shallower pool, better in the US, none in Canada. Extension, step out wildcats, 42% in the US, 68% in Canada. New field wildcats, so sort of really looking into unexplored areas, 14% in US, 30% in Canada. All exploratory wells, 30% probability of success in the US, 56% chance in Canada. And then for development wells, so for a development well, you're drilling in a place where there's already been oil discovered or gas discovered. So as you can expect, a lot of those geologic uncertainties, mostly source rock and migration, they kind of go to one. So then you can see the risking on it, the probability of success goes to 0.79 and 85% chance of success. So a big difference between exploration and development. And there's also a difference country to country, just because of the maturity of the basins and the technologies that's being used. If we look at Australia, for example, so this is back to 1960s data. So green is the exploration wells that were drilled, and brown is the discoveries. And so you can see that from 1960, probably back to 1950, up until almost the 1980s, it was less than 10% success. But then as more wells got added, as more information got collected, you can see that through the 80s and into the 90s, the actual exploration success rate went up to 30%. And again, we're talking combination of geologic success and commercial success. And then if you split that out, again, this is Australia data, onshore, offshore, 98 to 2006. You can see that the offshore success rate was around 25, 30%. Onshore went to about 50%. And again, use of technology, more wells being drilled, more data being collected. Really, so the risk in a basin can change over time. I see Brian asked here, any chance to get your slides? It's difficult following with just the presentation. The video quality does enable me to see the figures. Okay. Yeah, Brian, we'll try and figure something out there. Like I say, on YouTube, I think it's a little bit easier to kind of see it, but we'll see if we can figure out a way to get these slides. Well, I can send these slides to you, but for everybody else as well. So as you can see, there is quite a bit of variation in geologic risk and in exploration results. So we focused a lot on probability of geologic success. We didn't talk about commercial success. So again, that formula for geologic success, you're just multiplying the probabilities. But if there's oil and gas there, and we're going to talk about this more next week, if you've encountered oil and gas, you got all of this right. You had the source rock, you had the migration path, you had the trap, you had the reservoir, you had the good seal. All that stuff goes good. Now you've got hydrocarbon. So you've got a geologic success. To make it a commercial success, you need to have reserves and enough reserves to make it commercial. And we'll get into this next week. How much reserves do you have is really about the probability of recovering it. So, and this goes into the reservoir engineering side, where we're looking at proven, probable, and possible reserves. And those are official categories that the stock market uses to value a company. But really the way to think about it is proven. There's a 90% chance that you're going to be able to recover that much reserves. So it's proven. 90% chance that the reserves are there and you're going to be able to produce them commercially. Probable is about a 50% chance that you're going to be able to recover that amount of reserves. So in this example, it'd be like 66 million is proven, 70 million barrels is probable. There's 5 million barrels there that there's a 50% chance you could get it. Then possible, or 3P, is out here. There's a 10% chance that you can recover this. And that's, in this example, 80 million barrels. So the shape of this curve has a lot to do with the reservoir properties and a lot of the geology itself. But again, we just treated it as a productive well is going to give you this much. But there's actually a range on how much you can recover from an oil and gas well. And again, that's another application of probabilities. So, but that's for next week. Yeah. So if there's no other questions, may the odds forever be in your favor. And we'll talk more on probabilities next week, especially when it comes to distribution of oil and gas reserves. Okay, thanks everybody. Good night.